which have slides here.
Yeah, I've updated the slides on the Google Drive, so you can, if you want, you can access them with the latest version. No, I give you that. Okay, so I'll start. So I'm here with my second talk here on bending loss FEM simulation. And so just a very basic introduction. So what do you mean by bending loss? So it refers to the attenuation or reduction in the power of light as it propagates through a curved section of an optical waveguide. And it occurs because the guided mode is displaced towards the outer edge of the bend, causing energy leakage to the cladding of the surrounding medium. So basically, if you have a straight waveguide, like I showed here, you will have a uniform, basically you can imagine the center of mass of the optical mode is basically at the center of the waveguide, if it is a linear straight waveguide. But if it is a curved waveguide, you can imagine that the whole center of mass shifts towards, it's like a centrifugal force shifting is towards the outer edge of your waveguide. So you can see here, this is the waveguide and your center of mass is towards the outer edge. So that's what happens. And if you remember the earlier talk given by Sasha in the morning about Kerr-Combs, this becomes an important factor when you have to estimate the loss in your cavity. So the loss in the cavity in a macroresonator, one is the material loss in itself. So something comes from even from the fabrication side, some impurity, something that's not under your control. But also the loss can be minimized from your design perspective. So you can minimize the bending, the loss that is happening and you can improve the loss parameters by having better design. So the motivation is the main motivation, and actually much would be spoken also. So I missed a part. This talk will be given by two people, one me and one Zihan, who is sitting at the back. He is also going to give basically an advanced version of bending loss on an advanced structure, which is based on silicon nitride as well as lithium niobate. So, and he will explain that in detail. I won't go there. I will start from the basic, and then he will do an exercise, and then he'll give a talk, and then he will do an exercise. So, as shown by Sasha in the morning, so this is basically a paper from our group, Maxime Karpov earlier, who actually made these devices and generated soliton and multi-state soliton at 1 micron. And you can see that this resonator, the scale is, the whole diameter is 20 micron. This is a very tight, this is small resonator with FSR of 1 terahertz. So you can imagine that if you want to design 1 terahertz rings, how thick your waveguide should be. You cannot make a thin waveguide. Otherwise, your mode will just go out or probably your mode will not exist, the mode that you want to, the fundamental mode. There is a cutoff of the fundamental mode. So you need to very well calculate the bending loss because that contributes to your kappa knot. So as Sasha in the morning explained about the single photon frequency shift, Kerr frequency shift, which is dependent on the inversely proportional of the mode volume of a macroresonator. So 1 terahertz is interesting because that can help you generate soliton easily. And hence, there you need to have the right parameter of your waveguide so that you can minimize the bending loss. Another good application to minimize bending loss is to actually design lasers. There are I purposely chose two very opposite examples. In case of microresonator frequency comb, you would like to exploit the non-linearity of the material. So you want more percentage of your optical mode to be inside the core, inside the Chi3 material. So that's why you need thicker waveguides, and thicker waveguides can help you design tighter resonators, and you can exploit the non-linearity of the material. Whereas in case of, if you want to design lasers, low noise lasers, on-chip lasers, there you actually don't want any four-way mixing happening. You don't want any parametric oscillation. You don't want any frequency combs. You want a low noise single frequency lasing. So there you actually want to design, you don't want to exploit the Chi3 properties of the material. So you design low confinement waveguides. And there, if your waveguide is thin like this, this is a paper by the group of John Bowers, published in Nature Photonics, heavily cited. And then you can see that they have a very, very thin waveguide, 100 nanometer thin, and then you can see how wide this waveguide is, 8 micron wide, to minimize the bending loss. You can also see the scale of the whole wafer. This is 1 centimeter. So basically, the one device is almost a centimeter long devices. The whole resolators are pretty big. This is almost 1 millimeter. Here you see 10 micron. This is 1 millimeter. So these parameters need to be noted when you design such devices, and primarily it comes from the estimation of bending loss. So it's a very simple mathematics to calculate, to estimate bending loss. The electric field of a monochromatic wave, they're calculated in this manner, and you can actually separate the propagation constant in real and the imaginary terms. And if you separate them, the pure form in the imaginary part is basically the phase information, whereas the term which is attenuating the intensity, the power, is the attenuation constant, which is minus k imaginary part dot product the radial vector. And the attenuation constant, basically we have to convert electric field to intensity, and it becomes a factor of 2 here. This therefore this, and in dB per meter, you have this simple formula, and all converts your per meter to dB per meter. And so this is a small over that you can actually see how you get this factor 10 log convert dB per meter. And then it is also seen that your attenuation constant varies exponentially with radius. So smaller the radius, higher will be the exponential the attenuation constant. So a tight radii, a small radius will have like it rises exponentially, whereas the steeper is negative. So there is like an inverse proportion with radius loss, bending loss. So now I would like to turn to how to estimate such bending loss. So if you can actually, because there are 2 talks and we have 1.5 hours, so we can actually simultaneously do the exercise, and then I'll give you an exercise which you can actually estimate the bending loss, and then we plot, and we can also compare to one of the published result at the end. So let's, if you can access the Google Drive, there is a file of like with my name, bending loss SOLIFEM workshop. You can open that one. So have you all guys, all of you have that file open? Yeah? Not yet? Can you help me, Rishwan? This is COMSOL file. It's a COMSOL file. There are 2. So there is one bending loss underscore ln. Don't open that. That is the next one. So open the other one. Okay. So in the previous, so I would just like to ask a question. In the previous exercise, you must have been familiar with how to basically make a waveguide, right? How to set up a geometry. Is it all? It must be clear, right? To make a core waveguide and cladding. Okay, so basically, I'm not going like from a very scratch model, like open the model, drawing the rectangle. That will take a whole 1 hour then. And then Zion cannot finish his talk. So that's why I made that file where the structure is made, and you will have to run the simulation. I will make you understand what is going on. It's pretty basic. We need to open a window. That's gone. Okay. So I'll start then. Okay. So I'll assume everyone has opened the COMSOL file. Fine. So in the COMSOL file, you see a simulation, like if you click on geometry, you will see a waveguide like this. So here what you see there is like the cladding, the total cladding, the waveguide, which is 200 nanometer thin. I've specially chosen a thin waveguide because thin waveguide can easily show you a thicker waveguide, even 1 terahertz. Basically, you can design. I just showed you that there is a like Soliton work done with 1 terahertz resonator. So the bending loss there is not even higher in 1 terahertz. So you won't get the bending loss can be assumed as negligible. Hence, the bending loss comes into picture when the waveguides are thinner. Therefore, this can give you a better estimation. So here you have a thin waveguide. You can all set and then if you click on the parameters in the COMSOL, these values are entered, where the waveguide width is 1.5 micron wide. Your thickness of your waveguide is 200 nanometer. The bottom cladding and the top cladding is mentioned, which is like 10 micron bottom cladding, means that your waveguide, the bottom below this is basically silicon substrate. Then you have a bottom cladding of silicon oxide. Then you have a deposition of a silicon nitride, and then a deposition of a top cladding of 3 micron. And then this is air. So the whole structure is there. So even I included air. And this is the wavelength. So we will operate our simulation on at 1550 nanometers. And this I'll just explain what is this PML. I'll explain it. Okay, this is already clear to you, I think, from the previous course. So what is PML? PML is a called perfectly matched layer. And what does it do? So it is you can assume it is an artificial absorbing layer that actually mimics an open infinite space by absorbing outgoing radiation without reflecting it back to the waveguide. Because if you have a simulation model, a numerical model, and you don't, and not all simulation needs a PML layer, first of all. So you have to think that a simulation that you can see that there is some radiating modes, and if you don't have a PML layer and you have a finite boundary condition without a PML layer, then this can act as a reflecting boundary, and you can get interference on the reflecting layer, and then you will not get the real solution. So because you are operating with bending modes, so you have radiating modes, and you want the radiating mode not to reflect back. So PML layer basically acts like as an artificial absorbing layer, and without an appropriate boundary condition, the radiation would reflect off the boundaries. That's what I said, and re-enter the waveguide, corrupting the results. And typically, the rule of thumb is that your thickness of a PML layer should be of this, not hard and fast rule, but rule of thumb is lambda naught by n. And hence, I put there. If you go to the previous slide, I placed PML as wavelength by 1.5. So why 1.5? Because the outer, so here your refractive index is basically glass. So I just put 1.5. So wavelength by 1.5 the thickness of a PML layer. That's what perfectly matched layer is required for. And yeah. Okay. I think in the also in the previous exercise, you might have also learned about this. I'm just repeating it very quickly. The material selection. So in our case, we have three. We have silicon oxide, which is the cladding. Anything outside the core. Our core is silicon nitride, and there we have third is air. We have also included air. So actually, to real life like simulation. So I've also included air. Even if you don't have air, you can estimate it. I just added it. So we have seen in our group and our fabrication team, actually, this is our very internal, like the way we do in our lab. So our fabrication team have done the analysis by ellipsometry of the material analysis of silicon nitride, and they have advised us not to use the silicon nitride library of COMSOL. Instead, we use the Selmius equation of that basically helps us to estimate more correctly. That's why we use it. It depends on from foundry to foundry, but that's in our case. So we have this particular Selmius equation for silicon nitride, and I just added it here so that one can copy paste it from there into your simulation model. So for silicon nitride, I didn't add from COMSOL library. I just added a blank material, and the blank material under the property, I added this the variable refractive index of silicon nitride, which is actually added here under the component definition variables and you can see that the whole shell matrix is added, and this variable is then inputted here. That's how it is. Just the whole thing is set up. Any questions so far? It's fine. Okay. So moving on now, pretty simple. We are setting up the study. So what do we want to do? First of all, that we should know. So we have a definite. So in the previous, I think I forgot to mention the radius of the silicon nitride. So what the radius I have set? I have set the radius of silicon nitride 75 micron radius. So in order to estimate the bending loss, or if you want to basically say the cutoff bending radii. So like someone asks you that what would be the minimum bending radii you can design on a 200 nanometer thin platform. So below which basically you won't find any more. So you have a cutoff bending radii. You can not make smaller than this. The whole idea of photonic integration is to make smaller devices. So that's why it is important to know the minimum radii you can design. And to estimate it, I showed you that it has an exponential dependence on radii. So you know that mathematically you need 3 points basically to draw the whole exponential curve, and then you can basically get any radii. So we will estimate the bending loss for 3 radii and then fit it with an exponential, and we do exponential fitting and then plot it, and thus we can know, and then we can set in our mind that what is the bending loss cutoff you have set for yourself. So is it 0.1 d per meter you want to set, or 1 d per meter, depends on what you want. So ideally we would set to 0.1 d per meter bending losses. So yeah, going forward, so now this is already set. I've spoken about the perfectly matched layer. So how to set it up? One thing is to define in the parameter list just the variable, the thickness of the PML layer. So I have defined as a lambda by L, lambda by 1.5. And then if you go to definition artificial domain, here you can actually, here you can actually select which layers you want to select as a PML. And how to draw these things is basically very simple. In the rectangle part, you can actually have layer option there. And it actually tells you where do you want, left, right, bottom, top. So it tells you which one do you want. And there you can go to that rectangle and tell it right, left, bottom, this rectangle, right and left, this top, right and left. So that's how the whole thing is drawn. And then you go to artificial domain, you right click it, you will select it. They have various artificial domains, one of which is perfectly matched there. You go there and then you select all of it to make that perfectly matched layer. Yes, and then we have done the material selection. Okay, now setting up the study. Actually, before setting up the study, you would also like to put the mesh conditions. So all the mesh conditions are made there in your simulation. You can see. So that's I think already been spoken in the previous exercise. Nothing special here. So because your core waveguide is very small, there you would want a finer mesh, obviously. And then your because your cladding is so wide, so a bit coarser mesh. And for EPFL layer, I have used some mapped mesh. You can use other kinds of mesh also, but it is recommended to use mapped meshing, which is like rectangular, because you can see that it's different from the other meshes. Other meshes are triangular. That is like rectangular, evenly spaced mesh, because that's acting as the absorbing impression. It has to act in form of parallel interfaces. So for that reason, but it works for the other cases also. But I'm just trying to show you the very right. So to have map meshing in your PML layer. So the mesh is done, your material selection is done. Now setting up the study. So you can do this mode analysis in the parametric sweep. So first, the parametric sweep is what? We are only sweeping our radii. So we will sweep for 200 nanometer, we will sweep 75 micron radii, then a slightly bigger radius, you will take 150, then you will take, say, 200. So we will take 75 micron, 150 micron, 200 micron radii, calculate the losses. So as you increase the radii, you will assume the losses should go down, because now it is fairly big, your bending is not too tight, your mode is not interacting much with the sidewall, the losses are less. So you should be clear here that here the bending laws is simply calculated from the imaginary part of the refractive index. This is nothing to do with the scattering loss. Scattering loss is something different then. That is a different subject, different model is there to do the simulation. That also contributes to your intrinsic loss parameters, but we are not talking about that. It's just bending loss and purely because of the radii of the resonator. So, and now another part here which is important, which is common with also with what Zian will say later, that you have to simulate for a very large number of modes. You have to be very clear here that if you make your mesh very, very fine, you will take a lot of time to simulate. So whatever mesh parameters I have added here, it's already tested. The whole simulation with like 40 modes. You will simulate 40 modes because a lot of modes you will see yourself now that it will actually calculate on the edges, in the cladding. So because it's those modes, it's like the whole radii has a tight bend. There are a lot of mode which can go, which the whole structure can have. And hence it will show a lot, light number, we will have to calculate a lot of modes to actually get the right mode, which is inside the code. Now, actually, I have another question. Basically, Zian has already done this in his model. So I have another question. Can you tell me what can be another medium? So suppose if you simulate a lot of modes, how do you know which one is? How will you know that which mode is actually the one that you want to use? So there will be modes like outside your core. It will be here and there. So either you see and check. But suppose you want to have a whole automated model where you want to tell the computer that select this, select that. So of course, see and check you can do. You can go one by one, see which one mode is inside the core. You will select that. That's fine. And we can do that here also. So actually, right now, it is like that. I have not added that question, the answer to the question which I'm asking. So you can individually choose which mode you want. But if you want to know, like suppose you want to tell the computer, make a whole automated model, then what parameter would you select to actually know? Sorry? Yeah, effective refractive index, correct. One of which, so effective refractive index automatically comes when you simulate 40 model, but the effective refractive index is like you will have various values, and then it makes sense in the way that the largest effective refractive index will be the solution, because you can imagine the whole mode is inside the silicon nitride, so effective refractive index is largest, correct. But still, I think there could be other modes which can have nearby same refractive index. If it's too thin waveguide, too thin is like moldy, everything is oxide. So then what will you do? Smallest effective area. Yeah. That also, yes, because other modes are quite big, they will be. But then how will you calculate it? That's one way. Probably I would say a bit tough to estimate then. The one way, the easier way would be just to calculate the confinement ratio. So if you have a waveguide, just tell me, I'll ask the COMSOL to tell me how much of the electric field is inside the core. So if it is like, there is a real number and it is a the largest amount of electric field will actually tell you that the mode is there. Otherwise it will be like 0 or whatever, very less. So yes, so that's the thing. And in the material, I just wanted to know. Okay. Yeah. Okay, here also I think Zeru must have mentioned that in the axial symmetric model of COMSOL, your effective index is actually multiplied by the radius, and still it calls itself the effective index. So you need to be careful that in COMSOL, n effective multiplied by r is an effective. So it just multiplies by it. It just multiplies by r and still calls it an effective in axial symmetric model. So that is why you see that in my setting of the parameter, search for modes around 1.54 into RS, radius of silicon nitride. Like if it is linear waveguide, you would have only said find modes around 1.5 or 1.5 or whatever. But you multiply by the radius. That's how you do in COMSOL. COMSOL has, you have to do this. So that needs to be taken into account in all axial symmetric models. So yeah, actually I've written here, that's what I was finding. So when finding more than 2D axisymmetric, instead of finding an effective, the study will actually find an effective multiplied by R, even though it will still call it an effective. That's the COMSOL thing. Okay, so far we have done. So now I would like to actually for you to know if how many of you are like a little bit aware of COMSOL, have like done some COMSOL simulation? Little bit? Okay. So if I ask you to add that mode confinement thing which I was talking about, would you be able to add it? The mode confinement. So if you can just add the mode if I ask you just calculate the mode confinement percentage, would you be able to add it right now? So basically, I'll just tell you, I can actually show you after that, just like complete it. So you can add a domain and then we can calculate the mode confinement ratio, or actually Zian will actually show you in detail also later. So now after you've done the simulation, you in the derived results, you can go to global evaluation and there you can actually add. Basically I just you copy paste this particular formula, which is the formula which I showed in the first slide, into your derived results, and there then you just save it there. You run the simulation and then you run this, so it will calculate the dB per meter loss through bending. That will do. So now I will just ask you to
You can not you can like delete this ratio of phone, and you can in the unit section you can type dB per meter and so
I can do it. Actually, there's another trick. Don't do any of this. Actually, there's an inbuilt. There's also an inbuilt bending loss, EWFD, damp, something like that in COMSOL. But this is actually the real mathematics, so it's better to understand what's happening. But yeah, what Miguel is saying that instead of 20 log 10, or I think 10 log 10, because 22 comes from the intensity multiplication, that if you remove it, and just instead of that, put dB per meter here. So then it automatically converts. But anyway, you can play with it. It's like with you right now. So what I will do right now, so if you go to study, if you go to your study, go to parametric sweep, and can you check that this radius of silicon nitride is entered as such 75, 100, 150? Okay, so now just compute. It should take a minute. That's how what happened in my simulations. Is it running? For all of you, it is running? Okay, good. Is it finished for anyone? Over a minute? Over half. Over half already. Okay, good. I'll share it again. Okay, I'll share it again. It's fine. Okay. So you see it, right? Not yet. This is, you should not compare with it. This is a separate thing, but I just want first you to check yours. Man, shit. Someone has to stop COMSOL. Anyway, you guys are running, right? Yeah, someone if you close it, will take it. License. Simon, if you can write a message in the towns frequency code. Anyway, this is not right now not necessary. So, as for anyone, is done? Yeah, done. Okay, so can you go to this part like sorry, if you go down the results, electric field, and there you can just select on the right side, select which radius, and you have 40 modes for all the 3 radii each. So you can select and see how the modes are looking. Can you see the modes? So if you go to electric field, actually it runs when it is done. Anyway, it's fine. I'll just. Do you see the electric field? Yeah. Yeah, so different. So now for any area, go to the last refractive index. Like you said, the highest refractive index. If you go there, yeah. No, you select one arc and then change the different effective index and see how it looks like. Yeah. Yeah, but you need it, right? Okay. Let's try to stop it. I think even Simone did that already. Huh? No. Okay, well, I'll come to you. Yeah, so you have complete. So, when you are changing the radius, you are actually changing the window. So, you have to go and click this part, this circle, this square, when you change the radius. So, change it. No, yeah, so see height, but it's not height, it's like it was moved. You have to go here. Yeah, then now what I want you any modes?
Yeah, this is where is this
For example, if you do the last mode here, I have this mode. See, this kind of mode, like this is the same mode. Maybe after the mesh, maybe that was the issue. So let's see. It's already custom, but it's good idea, but it has to find I don't have that. So I won't probably do this with the trial version of COMSOL. So if you guys go to study, I see I don't have any warning. I saw warning in your guys simulation. So if you go mode analysis, I have transform. So effective mode index, mode search method manual, RPAC. Like this is my. You don't have such options. Yeah, round shooter rectangle. I just saw that. I don't know.
Around
Because you guys have warnings, right? There's a warning there. You don't have warning? You have a warning? You have a warning?
Really could not find most because we have like 4 points in your way. Was not upgraded. We had 13 iteration every 2 hours. That's but now it's going to be slow. This one.
But that is for a different sequence. If I make 1.54, or the same. No, you can try the different refractor index if you make it 1.52 or 5.1. And you can
I mean, why
So I think
but you know, you can
yeah, I think that is the COMSOL version here, which is probably causing the issue. The same thing, I would have the rectangle or a round shift, but I would just like to conclude it faster because then Zihan has another thing, and then we can check both simulations later, so that we don't waste the main talk. Okay. Yes. No, so the manual means that I have asked it to select, like I have given the manual instruction of where to find the index, around which value.
Where?
So I don't.
That's strange.
Search for what's around.
Yes. This is for a different thickness. For your thickness, this is 100 nanometer. So for your thickness, I have put 1.54. Because there is more silicon nitride, more thicker one. This is for 100 nanometer. This was the question I have made for thickness. So we can change that. You can see the values. Maybe we can all try with the final minutes later because Jan also has a talk. So I'll just conclude, and then because this I can show you what happens. And then we can actually work on the exercise because the model is there, and we can then stay and have question and answer now. So basically, as I've said, that in the global evaluation, we have added this particular formula, and then if you have, so I'm taking the last index. In your case, you don't see a guided mode. In my case, I can show that if I have electric field and I have electric field, I go to my solution, I choose any refractive radii. This is for a 100 nanometer thin, so this is not exactly yours. When I'm thin, I can see that there is I can go to the last one, which is the largest, I plot it, and I have a guided mode. I change the radii, and then I go to the last, and then again, so it shifts to a different radii, and there is a guided mode. So similarly, for all 3 radii, I have guided modes, And if I go to the global evaluation, now I select all parameters, all radii. The parameter is the radii. Then I select the last effective mode index, and then I just compute. So you get a table with 150 nanometer in all of them, with the second column as effective mode index. This is what I wanted to calculate. I will show you after Zihan's talk, the mode confinement, and this is the dB per meter bending loss. Now, since you have all of this, you can actually export it and save it. You can export and save it. I've actually already saved it, and I've also uploaded the MATLAB file which I did the curve fitting. It's a simple code, just does a curve fitting of these three values, exponential fitting, and here it is. So in your case, I already had the result for 200 nanometer thin. This is just to read the table and just the curve fitting. So if I run it, it should run.
Stop share button.
Oh, stop share button. Yeah, so I don't know why it is there in the air. Yeah. So this is the log scale I have plotted. This is the bending loss for a 200 nanometer thin platform. This is the bending loss for 200 nanometer thin platform, where you can see that if you have 10 to the power 0, 1 dB per meter loss, for this, for around 100 micron, you can have that much loss. So if you have that much target, you should not go below this radii. All your radii should be greater than that to have lesser losses. So that's how you can get the bending loss. And I also have the result for 100 nanometer. So I just go back to the presentation quickly, just to conclude faster. Yeah, so yes. So if you see, this is the SI of the Hertz line width paper, the nature photonics paper in the group of Don Bowers. These are the plots they have made for 200 nanometer, 250 nanometer in their case, and 100 nanometer. And they show that if you make thicker, like from 40 is this one, very high bending losses, even for like this big radii, high bending losses are so thin, they are very high bending. So as we go thicker and thicker, we can make tighter and tighter radii. So that's what they show. So my objective was to replicate this graph, which they have put in the SI of the manuscript. So this simulation does that. So what you did right now is actually this plot. Almost like I did purposely change to 200 nanometer, you can make 250. It's basically this one. And the exercise that I made was to make 100 nanometer thin, change the waveguide width to 2.8 micron and run the same simulation. Then you should get this plot, this second plot. So this is for 100 nanometer, this is for near about 200 nanometer. These two things was actually the what you should obtain to the exercise. And actually, I'll show it to you personally. Like in the meantime, I would like to call Zihan, and so that he can finish his talk, and then you have the whole bending loss study, and then you can do it. So Zihan.